Right, fire pupils, next part of our recurrence relations topic, and this time we're looking at convergence and divergence. Okay, often referred to as looking at our limit. Okay, so we're going to look at our linear recurrence relation. So un plus 1 equals aun plus b. So that is our typical linear recurrence relation. And in particular, we'll look at our a value. Okay, and this convergence divergence all depends on this a value. If you have an a value in this first statement, when a is less than or equal to -1 or a is greater than or equal to 1, the sequence will diverge. What we mean by diverge, it will go on forever and ever and ever. So it will keep either increasing, keep getting bigger and bigger and bigger and bigger and bigger, and that will continue on forever, or it will decrease forever and ever and ever, and that will go on forever. Okay, and that's all dependent on that a value. So you can actually look at the recurrence relation at the beginning and be able to tell what's going to happen to our sequence. The other side of that would be if our a value falls in between -1 and 1. So it's -0 point something or 0 point something. Okay, the sequence will converge. Okay, and what we mean by converge is that it will tend to a limit. Okay, so it will go to a value and it will stick at that value. Okay, often we talk about in this situation some of the kind of common phrases that we would see. You might use the word eventually. So what would happen to the sequence eventually, or in the long run. Okay, and that will kind of change depending on the kind of the word in the question. That's a couple of things to look out for. Just going to investigate a couple of things just to show exactly how this comes about. Okay, so I'm just going to look at two different sequences and see what we've got. So in this first one, I'm going to look at one which has an a value which is greater than 1. The rest of it's not particularly important. So a value of 1.2, so it's greater than 1, so it falls within this divergence. Plus 10 is just a b value, and u0 is equals to 100. So let's put that into a calculator. If I was to put that into my calculator, I would put in 100 equals. That gets my starting value within my calculator. And then I want my answer times by 1.2 plus 10 equals. Okay, I'm just going to put that into my calculator, see how that looks, and work along with me. So 100 equals answer times 1.2 plus 10. That's me represented my sequence. And if I press equals, my 100 is turned into 130 for my first value. Again, 166, so increased ever so slightly. 209.2, 261.04. So if I continue to press equals, I'm getting a larger value every time, and actually it's jumping up bigger and bigger and bigger. So I can see just from going through a number of different examples that will never ever tend to a limit. I'll never get to a final point that it will stay the same value. If I look in my second example, and in my second example I'm going to pick one quite similar, but this time the 1.2 is going to change to 0.8. The rest of it is going to look exactly the same. If I put that into my calculator, it's going to look very, very similar. 100 equals into my calculator. That means the 100 is stored. And then my answer times by this time 0.8 plus 10 equals. Okay, set it again, work this along with me in your calculator. 100 equals, that's that stored. My answer button times 0.8 plus 10. Okay, so that 100 turns into U1 of 90. $82. It's getting smaller. It's actually going down, went down by 10, went down by 8. 75.6, so even less than 8. If that keeps going, I'll continually press my calculator. That's 6, 7, 8, 9, 10 times. It's going down to low 50s, and I'm going to continue to go, and it's looking as if it'll get to bang on 50. And if I continue doing that, I'll actually get that with a wee bit of success. Okay, if I look at my statement, and what would happen if I had a value of 50? Okay, if I had 0.8 times by 50 plus 10, 0.8, so 80% of 50 is 40 plus 10, and that's equal to 50. So you can imagine in my sequence that would just continually repeat. I would put 50 in, the next term out would be 50, etc, etc. So that gives an example of what exactly happens when we have a sequence which tends to a limit. It will get to a particular value and just keep recycling within our recurrence relation. Okay, looking at the actual limit side of things, we have a very short formula to be able to work out it involving the a and b value. So to be able to work out your limit, then you take your b value and divide it by 1 minus a, and that gets your limit very, very quickly. So again, let's have a very quick look just at the example that we've given. So L is equal to 10 over 1 minus 0.8, which equals to 10 over 0.2. You can put that into your calculator if you wish. Top and bottom by 10 would be 100 over 2, which is equal to 50. That just shows you that that formula works for the particular example that we've got. Okay, very important part of communicating your answer. When you use this calculation to qualify that you're able to use the formula, we state this statement here, that a limit exists because your a value is within the -1 and 1 parameters. Okay, so that's stated every time that you work through a limit calculation. Okay, so seeing this in action, very typical question. A sequence defined by the recurrence relation. Okay, so we have an a value of 0.4. We know by looking at it that a limit exists. Let's go through our calculation. So part A, we're given a u0 value, so similar to previous. Our u1 value is 0.4 over u0 plus 20, u1 being the next term in our sequence, 0.4 times the previous plus 20, which is 0.4 times by 800 plus 20. So setting up on the calculator, 800 is my starting value. Answer times by 0.4 plus 20. I can see that in my calculator, therefore I have 340. So quite a jump down. U2 is 0.4 of my previous term, which is U1 plus 20. So 0.4 lots of 340 plus 20. My calculator's already set up, so I just press equals I get, and I get 156. So calculate U2, U2 is 156. And in B, calculate the limit of the sequence. As we said, we spotted that the A value is 0.4 at the beginning, so we know our limit exists. We need to go to our highlighted bit and make that statement before we use our formula. A limit exists as, and our A value is 0.4, negative 1 is less than 0.4, which is less than 1. So L is B over 1 minus A. So there's my A value, and there's my B value. 20 over 1 minus 0.4. 20 over 0.6. Top and bottom by 10. 200 divided by 6. And that works out as 33 1/3. And again, as always, would want to keep that as accurate as possible. So that is an exact fraction. So it's not 33.3, it's 33 1/3. That's what our exact limit. Calculate the limit of the sequence, 33 1/3. Okay, very typical limit calculation. Remember, it in part B, it might state explicitly the limit, or it might talk about some of the wording and eventually in the long run, etc. Okay, slightly different question. In question 2, a sequence defined by a recurrence relation and has a given first term of U0. Given that the limit is 27, find the value of k. Okay, the fact that it's got a limit, then we can actually make the starting statement as a limit exists, negative 1 is less than k, which is less than 1. So I can make that statement right at the beginning. And I tend to go by hints, so there's a limit of 27. If I'm seeing any mention of limit, I know I want to go L is equal to B over 1 minus A, where my A value is unknown at the moment, it's K, and my B value is 2K. So 2K over 1 minus K. Okay, so I have a statement for my limit, and my limit is equal to 2k over 1 minus k, but my limit is also equal to 27. And that's given within my question. So if L is equal to 2k over 1 minus k and L is also equal to 27, therefore I can make the statement that 27 is equal to 2k over 1 minus k. And now I have an equation, one unknown, which is k, so I need to try and solve. So let's times top and bottom by 1 minus k. So 27 lots of 1 minus k is equal to 2k. As these two will cancel out. 27 minus 27k is 2k. Add 27k onto both sides. 27 is equal to 29k. And divide both sides by 29, so pen not working. My k value is 27 over 29. Keeping that as a fraction because that is my exact value. Okay, let's round off the question. Given that limit is 27, find the value of k for a limit of 27, k equals 27 over 29. Okay, so typical question in part A, sorry, question 1, working out a limit, and in question 2 is using, we've got a problem solving to be able to work out our k value or our a value in our linear sequence. Okay, as always, let's look at the PowerPoint for some questions.